Hello, this is Professor Dan Kernler of Elgin Community College with another video in my statistics series. This one is all going to be about the normal distribution. All right, let's get to it. You might recall in the past, we've looked at the shape of the distribution of some variables. For example, we have this children of immigrants, their distribution of SAT scores looks pretty bell-shaped. How about the heights of children aged 10 to 17? Again, pretty symmetric. This one is average class size, happens to be third grade average class size. In fact, if you put a little bell-shaped curve on top of this one, it seems to fit it pretty well. And we've actually talked about that bell-shaped curve when we did the empirical rule. If we have a distribution that happens to fit this perfect bell-shaped curve, we said, well, there should be 68% of the observations within 1 standard deviation, 95% within 2, and then 99.7% within 3. So the question we want to investigate, and I alluded to it back in that video, was, where did those percentages come from? How do they know that? And that's what we're going to talk about in this video. Before we can get to that, we have to build up a little theory. Remember the dice example where we threw 2 dice and we found the sum? We could have 2, 3, 4, etc. down to 12. If you make a graph of those probabilities, it looks something like this. It's actually called a probability histogram, where you have the sum of the two-sided dice is your horizontal axis, and then the probability is the vertical axis. So if we have a random variable, call it x is the sum of the 2 dice, we want to find the probability that x is less than or equal to 4. So you get a sum less than or equal to 4. Well, that would just be those 3 probabilities. The probability that it's 2, that's 1 out of 36. 3 is 2 out of 36, and 4 is 3 out of 36. You add those together, you get 1/6. Okay, now we're going to dive a little bit deeper and look at this a little bit differently. And instead of just adding the probabilities, what if we focus on the areas? So add up that first area, that first rectangle. It's 1 by 36. Second one is 1 by 2/36, and the third one is 1 by 3/36. So if we add up the areas of those rectangles, we get, of course, the same thing, but this area being probability is really important. And this is going to be the foundation for pretty much the rest of the course. The area underneath the probability density function is the probability of your variable being in that particular interval. All right, let's say we have a random variable. In fact, let's say we're looking at a random number generator, and we're generating a random number between 0 and 1. Any number between 0 and 1. So our number could be anywhere in this interval. Let's look at some probabilities. What if we want to know the probability that our randomly generated number is exactly 0.5? Well, the problem is our number could be any real number in that interval, and there are infinitely many of them. So we're looking for just one number, but there are infinitely many of them, so the probability of being exactly 1/2 is 0. It's impossible. It's impossible for a random number that could be any real number between 0 and 1 to land up exactly on 0.5. Okay, well, how do we get probabilities then? The key is to look at an interval. What if we look at, say, anything between 2/10 and 4/10? Well, now there's a width there of 2/10. There's a 2 out of 10 chance of getting a number between 2/10 and 4/10. Okay, continuing with this, again, we're trying to build up a really important conclusion here. Let's make a drawing of this one and try to get a probability density for this one. Since our number can be anything between 0 and 1, we really want to have a probability density that has 1 all the way across. That way, when we compute the area, we have this rectangle. Its width is 2/10, its height is 1, and so the area there is 2/10, which is that corresponding probability. Now this is kind of an unusual probability density function. Most variables don't have this equally likely density for the whole interval. Most variables, it varies along there. Certain intervals are more likely than others. The key here is that the area was 2/10. So that means that the probability was 2/10. Probability is area, area is probability. This is the big takeaway from this little investigation. What we're talking about is the probability density function. So along the x value on these will be all the possible values of your variable, and then the vertical axis is the probability density. Not saying the actual probability, because individual values here for continuous variables like we're talking about don't have probabilities, but there's an interval. So it's saying how dense is the probability near that. And we might have some curve say look something like this. Well, we know the total probability of all possible events must be 1. And we know that area is probability. Well, that means that the area under this curve must be 1. And this is true for all probability density functions. The area under the curve must be equal to 1. Suppose we look at a particular interval. There's a couple of different ways to interpret that. One is you get some number. It could mean that the proportion of all individuals is represented by that area. Or it could be what is the probability that one individual is in that particular interval. Okay, back to that empirical rule. This distribution, this is actually a probability distribution, and it's formally known as the normal distribution, where you have the mean in the middle, and then plus or minus 3 standard deviations get you all the way to the edge. Well, how do we find probabilities here? How do we know areas underneath it? Well, I have good news and bad news. Good news is there's actually a function for this curve. Bad news is it's a little crazy. And if you want to find the area between two particular values, say the area between x1 and x2, well, if you've had some calculus, you might remember this is actually an integral. We have to integrate this function from x1 to x2. Okay, before you panic, we actually have calculators that can do this for us. There's even tables that they used for years to do this. So we're not going to actually be doing integrals, for at least for my students. So let's talk about how to actually compute those probabilities. All right, the first way is actually on a table. I'm going to talk about this just for completeness sake. I do not want you using a table. Hopefully, if you're in a class, your professors don't want you to use a table. When I'm recording this, it's 2021. We should not be using tables anymore, but sometimes people still want you to do this. So what I have here, this is a table for the standard normal distribution. So there's that word standard there. Is that important? Yes, very important. So the standard normal distribution has a mean of 0 and a standard deviation of 1. For notation's sake, we use the letter Z for the standard normal distribution, and you might recall this. We used this for the number of standard deviations from the mean. That is relevant, and it'll come back as we go through this section and later sections as well. So in this case then, on the x-axis here, the z-axis we should say would be 0, and then plus or minus 1, 2, and 3. So if z represents number of standard deviations, on the standard normal distribution, the mean is 0 standard deviations from the mean. So that's 0, and then 1, 2, 3, etc. How do we use this table then? Well, if we zoom in and look at a particular number, here's this 0.0024. If you track over to the left and then up to the right, there's a negative 2.8, so that's to the 10th place, and then there's a 0.02 to the 100th place. This means the probability of being to the left, or the area to the left of this on the curve, of negative 2.82 is 0.0024. So the number in the middle represents the area or the probability, and then you have to track the numbers along the left represent the 10th place, and then the numbers along the top represent the 100th place. Again, my students, we're going to be using a calculator in StatCrunch. So let's do that next. It's pretty straightforward. The calculators, you've done this for binomial, so we're going to go stat, calculators, and then do normal. The default is the standard normal distribution, so you'll see 0 and 1. And we want to go less than or equal to negative 2.82. Hit compute, and then you get the 0.0024, just like we did on the table, but a little bit easier. We did previously talk about heights. We had heights of ages, children ages 10 to 12. This was in our health behaviors of school-age children. Let's look, in fact, at 12-year-old males. At the time of filming this video, I actually have a 12-year-old son. So this is pretty symmetric. It's not perfect, but if we draw a normal curve, It fits pretty close. Calculating the mean and standard deviation, we have a mean of 60.4, a standard deviation of 4.0. If we try to make our normal distribution then, 60.4 goes in the middle, and then all of the standard deviations, out 3 standard deviations, should be 4. And so if we add those together, here is our distribution of heights. We might then want to ask some questions. For example, say we look at 65 inches. We want to know what proportion of boys are taller than 65 inches. Or we could also ask the question, if I randomly select a 12-year-old boy, what is the probability that he will be taller than 65 inches? We can do this in StatCrunch. So all we do is we go to the stat calculator's normal again, enter in our mean at 60.4 and our standard deviation of 4, change the inequality to be greater than or equal to, type in our 65, hit compute, and there we go. So that means there must be about 0.125, about 12.5% of all 12-year-old boys are taller than 65 inches. Or, again, in terms of probability, the probability that a randomly selected 12-year-old boy is taller than 65 inches is 0.125. What if instead we know the probability and we want to find the corresponding value? So, say, for example, the 20th percentile. That's the value over there on the left that has 20% to the left, or an area of 0.2. This is just as easy in StatCrunch. We go back, we can go to that same calculator, in fact. We could put in the mean, put in the standard deviation, and now instead of entering in the inches, we enter in the probability, make sure the inequality is pointing to the left, hit compute, and then we can see that that 20th percentile is about 57 inches. Okay, one last topic. What if we have a very small data set like this one? Say we do some resting heart rate. We have people take their heart rate. We get these. It's difficult to do a histogram when you have a very small data set. But we still might want to know, hey, could this come from a normally distributed population? There is actually a way to check it. And there's a graph we can do, and we'll talk about how to interpret that. The basic idea is you have this z-score. Remember z, number of standard deviations, x minus the mean over the standard deviation. If we do some algebra here, say we multiply both sides by sigma, add mu, and then just kind of reframe this, then x should be mu plus sigma z. Now this might not seem very helpful. What we're going to do though is treat the z as the expected z-score if we had a sample size of 10. So then when we multiply by the standard deviation and add the mean, we get what the x should be if the values were normally distributed. And then we have the actual x values to compare. And what we're going to do is focus on that relationship between the expected x values and the actual x values. All right, let's talk about how to find those expected x values. If you think about your normal curve, let's say if we have a sample size of 10, that we can break it up and have 10% in each of these intervals, and we can use the normal calculator or whatever to calculate each of those corresponding z's. Just for illustration purposes, let's say we want to find the fourth x. Well, there should be 35% below and 65% above. And then we can use that to find the corresponding z. And then in our formula, x equals mu plus sigma z, we're going to calculate the expected x value. We'll plug in the mean and standard deviation, and this z that we calculated that corresponds to 35% below and 65% above. Simplify those, we get 83.2. Now the actual fourth one in order is 82. The expected one is 83.2. If we graph all of these, it looks something like this. And we would expect them to be equal, right? We would expect the actual x value and this expected, if it were normal, to be equal. And this is what the graph looks like. What we're looking for here is a line, or something very close to a line. It doesn't have to be perfectly linear, but especially in the middle, we want it to be very close to a line. In our particular case, it's pretty linear. Some programs actually add like a band, like a confidence band, where as long as you're within that band, it's okay. StatCrunch, unfortunately, does not, but there is a quick way to get this graph in StatCrunch. There's a specific graph set aside for this, and it's called the QQ plot. You have to go down the list, QQ plot. That's this plot that compares the expected x values with the actual x values from the data. And again, what you're looking for here is a line. You're looking for this to be fairly linear. Okay, that is it for this video. I hope you found this helpful. There was a lot in here. If you are interested in seeing more of these, you can subscribe, hit the bell to get notified. Also, a big thank you to the Elgin Community College Board of Trustees, which approved my sabbatical for the spring 2021 semester. And that's what gave me all the time that I needed to record, edit, and upload all of these videos. So thank you so much for watching, and I will see you in the next one.